In class activity 18D, drug concentrations. The concentration of a drug in the bloodstream can be approximated by a rational function of the form f of t equals at over bt squared plus 1, where a and b are parameters. 1. Based on your experience with scaling graphs, can you determine what will happen to the graph of f as the parameter a changes? Well, as a increases, the graph of f will expand vertically. As a decreases, the graph of f will compress vertically. Objectives for the activity. You will understand that rational functions can be used to model drug concentrations in bloodstreams. You will be able to use data points to match a model to data. Use a model to make predictions. Consider a fictitious drug called cordrazine. The concentration of cordrazine in the bloodstream, f of t, is measured in nanograms per milliliter and is modeled by the function f of t equals at over bt squared plus 1, where the independent variable t represents the number of hours after injection, and a and b represent positive parameters that depend on dosage. 2. In question 1, you thought about the effect of parameter A on the graph of f. Now we will think about the effect of parameter B on the graph of f. Part A. Based on your experience with shifting and scaling graphs, can you determine what happens as B changes? Well, the parameter B neither scales nor shifts the entire graph. So let's put that here. B. Scales. Part B, for fixed values of A and T, as B increases, what happens to f of t? Okay, to answer this for part B, let's bring up the calculator. I'm just going to go to the y equals screen. On line y1, I have the function entered in here, we're calling f of x. And I have for A, I have 1, and for B, I also just used 1, just to get a starting point. So if we were to graph this, this is what we see. And I'm even going to look at the top of this function, the max there. So when x is equal to 1, the output is a half, or 0.5. So that can be our starting point. And it says for part B, for fixed values of A and B, what happens as B increases, what happens to F? So let's go back to the y equals screen and look at the y3 line. Here I left the A as 1, so 1x is the numerator, just x. And then the B in the denominator is now 2. So I just doubled that and see what we come up with. I'm just going to graph it. And you see right here, it looks like the output has decreased. And not only has the output decreased, it's a little bit to the left of our previous output, which was right there. So it's a little bit to the left of 1, where x is equal to 1, and it's a little bit lower. So let's go back and write some of this down. For part B, for fixed values, let's see, by increasing, we increased B. So B, there we go. Increasing B causes f of, it's supposed to be a t, not an x, causes f of t to decrease. Okay, for part C, for fixed values of A and T, as B decreases, what happens to F? So let's go back and try to graph this. It's going to go back to the y equals screen. And what I'm going to do is turn on the y4 line, and you see the B in the denominator is now 0.5. So let's graph this and see what happens. Now, it looks like our output increased. And not only did it increase, it actually moved a little bit to the right. So the output went up and to the right, so the max did. And let's try another one of these, but first let's write this down. So for part C, we could say by decreasing B causes f of t to, we saw it increase. There we go. I'm going to scroll up to the next part, part D. It's going to go through the whole, well, not the whole page. I'll leave question 2 there. So for part D, it says, based on your observations, how does the value of B affect where the maximum of F occurs? Well, let's try this once more at least. And I'll go back to the Y equals screen. And I'm going to turn on, let's see. Let's do this. Well, let's go up to Y6. And we'll turn this on. And we should see the peak move up and also to the right if we are going to stay with this pattern. And you can see that's exactly what happened. The peak moved up vertically and it also moved to the right. So let's go back and put some of this on our part D part of the paper. As B increases, and as B increases, the maximum of F moves to the right. Whoops, that's not right. Do over. That should say as B increases, the maximum of F moves to the left. Sorry about that. And as B decreases, maximum of F moves right. There we go. Number 3, assume the concentration of cordrazine, peaks 1.2 hours after injection with a concentration of 3.2 nanograms per milliliter. Our goal is to find values of A and B that match the curve to this information. Part A, which parameter should you determine first? Okay, so let's work with B first. So let's determine the value of B. We know from what's given to us here is we want that the horizontal axis, the x-axis, or we're calling it the t-axis, to be at 1.2. So if we go back and just start experimenting with this on the line Y7, I just have, the one in for A and one in for B. And when we graph that, we get this curve here. And you can see the horizontal axis is at 1, so we get 1.5. So I want to move that to the right. So we saw earlier that if we decrease the B, we can move the x value or the t value to the right. So let's make this, it was at 1. Why don't we go to 0.9? Oops, that's not 0.9. This is pushing all the wrong buttons here. How about that? 0.9. There we go. And graph that. And let's see where well, it did move to the right. The x value or the t value did move to the right slightly. So let's continue. How about we go 0.8 and graph that and see what happens. Oops. Okay, it moved a little more to the right. So let's continue doing this. About 0.7. Oh, pretty close. 1.19. How about if we just make a little bit more adjustment? How about and let's see where we are. 1.20. Okay, so that looks good. So we sufficiently moved, sufficiently to the right on the horizontal axis. So let's go back and go to our Y7 line, and we'll move to the numerator. And we want to move this up, the output up on the vertical axis. And it's at 1 now. Why don't we just move it to, oh, let's go to 3 and see what happens. So I'm going to graph it. Whoops. So we're at 1.8. The output's 1.8. We have to go up farther than that. We have to go to 3.2. So why don't we go, let's see, we did 3. Why don't we try 5? Let's see what we come up with. Oh, it's getting pretty close. So it's at 3.0 almost. And we had to go to 3.2. So let's make one more adjustment. About looks like it'll do it. So or the t-value is 1.2 roughly, and the output is, if we round up, 3.2, 3.19. So let's go back and so we can see that the A is 5.3 and the B is 0.69. Okay, let's go back to our paper. Let's see. So we worked with B first, and then we found A to be about 5.3, and B was about 0.69. Part 4, use the parameters you found in question 3 to determine the concentration after 12 hours. Okay, so what we're looking for here is, I'm just going to write this down. We have 5.3 times 12 over 0.69 times 12 squared plus 1. So that's what I'm going to enter into the calculator and see how this works out. You get rid of the graph. Here we are. So we'll do parenthesis 5.3 times 12, 0.69 times 12 squared plus 1. I guess I didn't need the extra parenthesis, but let's see what happens. About 0.63. We'll just round it to 0.63. Let's go back here and write this down. 3. There we go. Part 5, I'm just going to scroll this up here. Part 5, it says use the parameters you found in question 3 to determine when the drug concentration reaches 1.6 and roughly the half-life of the drug. Okay. Okay, so what we'll be working with is, how about this, 5.3 t, that's the numerator, and then the denominator, 0.69, and then it's t squared, and then we have plus 1, and we want the output to be 1.6. So if we multiply this out, we're going to get a quadratic, and it's going to end up being 1.104, and that's t squared, minus 5.3 t, and then plus 1.6 equal to 0. And when we get our answers, we'll get 2 answers, but the answer we're looking for is this one. 4.48 is one of our answers, and that's about a little bit less than 4.5 hours. So that's about 4 hours, 29 minutes, and it's quadratic. So this actually ends up giving us 2 distinct values, or answers, and we'll get 0.32, which is about 19 minutes. And we're just going to discount this answer there. I mean, mathematically it's correct, but it doesn't make any sense in the context of this question. So we'll just go with this. Part 6, determine the half-life of the drug by finding the time it takes for the drug to drop from its maximum concentration to half of its maximum concentration. So we found, half-life, or roughly half-life. We got 4.48 minus 1.2, and that's going to give us roughly 3.28 hours. All right, that's the end of this video. Thanks.